Okay, let's start. We are close to the end. Only one talk left, and then it's free for everyone. So, fortunately, the title it's as you can see, there is the word generation and characterization of isolated attosecond pulses. So this is what I'm going to talk in the next, let's say, 40 minutes. Fine, Yanis? Okay. This is just a brief outline of the talk. So I will start from some general properties of the order harmonic generation. I guess you are already familiar with. Then I will switch to how it's possible to create using this process extreme broadband continua. Then how we can characterize, and I will finish the talk with some, let's say, now no longer so recent results which have been obtained at free electron laser, this time not yet Fermi, but at SLAC. The free electron laser in Stanford, because there they can generate isolated attosecond pulse. So let's start with some fundamental properties of the order harmonic generation process connected to the generation of isolated attosecond pulse. I start with these slides that I guess you're probably familiar with by now. This is a typical spectrum acquired with a multi-cycle pulse. So in which we have, discrete order harmonics of the fundamental radiation. And here on the left, I reported what we will know the freestyle model, which is used in order to interpret the generation of harmonics with the process of tunneling, ionization, acceleration of the electron in the continuum, and their recombination. In red, we have the two optical cycle actually of the driving field. And these two curves that you can see here, these are the ionization times and the recombination times with the two quantum paths for each half optical cycle. Okay, so essentially the electron, in order to get a certain photon energy, can tunnel through the potential barrier at this time, and then it will recombine at a later point here. This is one possibility corresponding to the short path, or it can tunnel out from this E prime SB and recombine later, and this will be the so-called long path. Okay, now, of course, maybe I can show here, you can see there is a point where this kind of bell-shaped curve reach a maximum. Here, this will depend on the intensity of the electric field, on the amplitude of the electric field. And as you know, in a pulse, this amplitude will follow, a certain envelope profile. So this is a crucial characteristic for one of the ways to create an isolated attosecond pulse. And just to show the idea here, I've reported, actually this is from a paper we did a long time ago. But these are just very simple simulation in which you really consider a pulse, a few cycle pulse. You consider all these ionization and recombination curves. The ionization are in red. In black one, we have the recombination. And you can see that the maximum is following actually the amplitude of the electric field, this Gaussian-like profile here. Now, if you look in particular to the highest harmonic order, let's say around 75 to 90 here in this region, you see that we have just two paths contributing here. You can also see this on this part, where you have the harmonic order and yet the emission rate associated to the different curves here. You see, in this region between 75 and 90, you will have only this one and this other one. So what we learned in this way, we learned that if we start considering or using very short pulses, and I will start using the term few cycle pulses, so pulses which comprise only few oscillation of the electric field, we can confine the harmonic generation to only few trajectories. In this case, two. If we do things in the proper way, in the sense that if we shorten even more the pulse duration, we also control the carrier envelope phase, we can really confine the harmonic generation to a single half optical cycle. And this is a kind of prerequisite for creating an isolated attosecond pulse. Okay, so this is just to point out that the key point is to have very short pulses, few cycle pulses. This is a way to create a broadband continua that I will indicate as temporal gating. Another one is to use another fundamental property of the process of the harmonic generation, which is the dependence on the harmonic field on the polarization state of the driving field. Namely, if you have linearly polarized pulses like this white one, what you can have, also according to the simple three-step model, is that the electron will tunnel out, will be accelerated from the electric field, and then because the electron is moving ideally along a line, when the electric field is changing this sign, it will recollide the electron back to the parent ion, and then recombination is possible, and the photon will be emitted. However, if you have a securely polarized pulse, well, the electron can still tunnel out from the atom, but because we have a transverse momentum, in general, the electron will never return on the parent ion, and we will not have harmonic generation. Recombination is not possible. So the idea, and we will see later how to implement this, is to create a pulse which is somehow a mixture of these two states. Okay, so where we have a kind of ultra-fast transition from a pulse which is equally polarized to a pulse which is linearly polarized. Okay, we will see how the shape of this electric field looks like. This is another way to confining the harmonic generation, which is usually indicated as polarization dt. Okay, now let's see how really look these ultra broadband XUV continue, how they look like. Let's start with the polarization gating. So the original idea actually is from Paul Korkum and also from Misha Ivanov, who really, and I think this is really the first one of the first idea on how to create an isolated attosecond pulse. The pulse we want to create is essentially this one. This is how the electric field looks like, and you see, essentially we have the following. On this side, we have a circularly polarized radiation on the leading edge. On the trailing edge here, we have again a circularly polarized radiation with opposite helicity. And in between, we have a region where the pulse is quickly switching to elliptically polarized, and then here in the center, linearly polarized. In this paper, they suggest creating these funny polarization states using two OPAs with a slightly different frequency. This is one possibility. A more practical one is what was introduced by Rick Constant a few years ago using birefringent plates. So one can exploit birefringent plates in order to create this polarization state of light. The other possibility, which we were discussing before, to create a broadband continua, is to use very short pulses. And now we really go to few cycle pulses. So now these are a simulation in which you see the transition of the harmonic spectrum using a 10 femtosecond pulse and a 5 femtosecond pulse driving grid. Now we have pulses with linear polarization. And you can see that for the 10 femtoseconds, we have that spectrum, it's always, let's say, modulated up to the cutoff, while for the 5 femtosecond pulse, we have a region in which the spectrum looks more or less continuous. And this is, again, a prerequisite for creating an isolated attosecond pulse. And the corresponding temporal structure for different selection of the harmonic spectrum. You can see here in the very high energy region, one can really isolate a single pulse. So in both cases, you see, the fundamental condition is to have short pulses, few optical cycles. So how we can generate this? The first way that was demonstrated to create these few cycle pulses, is the hollow fiber compression technique, which was demonstrated by Mauro Nisoli and co-workers in the Technical University in Milan. Essentially, you start with a titanium sapphire laser system, 25 femtosecond pulses. This is commercially available, and you couple this inside an hollow waveguide. So it's a capillary that you fill with, in this case, with argon at a certain pressure, typically few hundreds of millibar up to a few bar. And because of self-phase modulation, you will broaden the spectrum. And then you can temporarily compress the spectrum using Chern mirror. In this way, one can rather easily reach a compression factor of 5, 6, or even larger So one can really create, pulses which have a duration of 5 femtoseconds or even lower. Now, if you consider that the optical period at 800 nanometer, it's about 2.6 femtoseconds, you immediately see that you have just a couple of full optical oscillation underneath the temporal envelopes, and that's why we talk about few optical cycle pulses. So now, there are, of course, other systems in order to create these few optical cycle pulses. One can use a multipass cell or a cascade multipass cell, which also gives the possibility to have, a much higher throughput. Okay. The other important aspect, which I have not read so far, is the carrier envelope phase. So one needs to control not only the pulse duration, but also the precise electric field of the laser pulse. You have seen that the typical way to describe an optical pulse is to have a product of an envelope. This can be a Gaussian times a carrier wave. This phi represents the carrier envelope phase. And it's essentially nothing else than the temporal offset between the maximum of the envelope, which of course is equal to 0, and the maximum of the carrier wave. Now, this is typically a parameter which it's not relevant if you have multi-optical cycle pulses. It starts playing an important role when we have only few optical oscillations. And you can see here, for example, here in this case, we are considering just to show you the importance, a perfect cosine pulse. So we have that the maximum here of the field in the upwards direction, it's larger than the amplitude of the field in the downwards direction. So we have an asymmetric pulse pointing in the upwards direction. If p equals to pi, we have exactly the same situation, but in the opposite direction. And then in between, we have the case in which p equals pi over 2, which is perfectly symmetric. So the amplitude in the upward direction will be exactly the same in the modulus of the amplitude in the downward direction. Okay. Now, if you start having few cycle pulses which have carrier envelope phase stabilization, you will start observing different XUV spectra depending on the CP. This is a spectrum that you acquired now a few years ago. And you can see here that, for example, if equal pi over 2, we have a modulated spectrum up to the cutoff, while the modulation is much less pronounced. We have almost a continuum if you have equal to 0. So and that's why it's important to control the carrier envelope if you want to synthesize a continuum. The very first, of course, result was obtained regarding the influence of the carrier envelope phase on the XUV spectrum. Beautiful results were obtained by Ferenckrauts and Andrus Baltuska, I think in 2003, if I'm not mistaken. And you can clearly see the effect of the carrier envelope phase in the cutoff. You see, if P is equal to an unknown phase plus 0, you have a smooth spectrum here, while if you change the phase of pi over 2, you get nice harmonic modulation. So in this case, we have at least 2 attosecond pulses created. In this case, very likely an isolated attosecond pulse. We also observed these effects, actually, Nico, clearly observed this. Nico was also part of the network. In 2006, a few years later, using the polarization gating technique. So using the combination of birefringent plates, it could synthesize a pulse with this funny polarization state, and controlling the carrier envelope phase, it was showing a clear transition from a highly modulated spectrum, the black one, you see here, to the yellow one, where we have, almost a perfect continuum. Okay, so these are different, both techniques in the temporal gating and in the polarization gating. We have that both ingredients, Q cycle pulses and CP control, are playing, a crucial role. And they are important they are crucial for creating these isolated attosecond pulses. Now, so far we are always talking about spectral intensity, right? So with also the measurement I show you are essentially reporting spectral intensity. But if you want to perform attosecond metrology, so if you want really to characterize the temporal structure of these pulses, we also need information about the phase. That's the tricky part. Because only when we combine the spectral intensity, which we can easily record with an XUV spectrometer, with the corresponding phase, we can reconstruct, just by Fourier transform, the temporal profile of the attosecond pulse. So how do we get now the temporal phase here? And the good point is that we can understand, how we get the temporal phase really using classical mechanics. We don't need to. We can, of course, there is also a quantum mechanical model, but the basic principle, which is typically indicating that attosecond strict camera can be really understood using classical mechanics. Classical mechanics and classical motion of a charged particle inside an external electric field. So the physical process that we are considering here is just our atom, which is irradiated with what we think is an isolated attosecond pulse, and at the same time, we irradiate the same atom with a replica of the infrared field which has created this isolated attosecond pulse. So the atom will be ionized by single photon absorption. We emit an electron in the continuum, and this electron will start feeling the effects of the infrared field. And will move according to this equation, which is nothing else than Newton's equation. So we have the mass of the electron, the acceleration, and here we have the charge and the external field, the infrared field. So you can easily calculate the acceleration, the velocity here, and also the final momentum of the electron. Once the electric field will fade away, will go to zero. So essentially what it's extremely simple math. What you will see is that the kinetic energy of the electron, the final one, is the kinetic energy that you will measure in your experiments, will be modulated by a term which is proportional to the velocity, initial velocity, the one at t equals 0, or t0, times the vector potential of the external electric field. So essentially, we have an energy modulation that depends on the vector potential at the ionization instant. Okay, and now I will just show you pictorially what we expect to observe. So keep in mind this equation here. What we have here on the left corner, it's our isolated attosecond pulse. Because of the three-step model and because of the different time of recombination, this energy will change through the spectrum here. So the pulses that we expect to measure are positively charged. Okay, that's why these different colors. We have the red first and then the blue. When we use this XUV pulse to photoionize an atom, essentially the photoelectron spectrum reproducing on the right that we will measure, it's, let's say, a replica of the original content of the XUV spectrum here. Okay, we get a kind of one-to-one mapping. Of course, we need to consider the cross-section of the atom, but will be more or less, a replica of that spectrum. Now we add the vector potential of the infrared field. So because of this equation, what we see is that the action of the vector potential is instead of adding a kick in the momentum space. So let's consider, for example, here we have a positive kick because the vector potential here times the charge is positive. So this photoelectron distribution will be upshifted by quantity which is proportional to the charge times the vector potential here. Okay. Then we change the delay between the isolated attosecond pulse and the vector potential. For example, let's consider the case where the ionization is taking place at the zero crossing of the vector potential. Okay? So now what we have is that the first part here of the pulse will create photoelectron with, let's say, low momentum, because we have the red component of the XUV spectrum, but these red components will receive an upkick because the vector potential is positive. On the other side, blue components means high photon energy, so here we have high momentum, but the vector potential is negative, so we receive a downtick by the external field. In other words, what you will have is a kind of compensation effect. These two slopes will compensate each other, and you expect to observe a photoelectron distribution which is not shifted in energy, but which looks like compressed in the momentum space. Okay, so that's why the width is smaller than the original one without infrared field, and because the total number of electrons, if you like to see in this way, must be conserved, the height should be larger. We change again the delay in these measurements. What we expect to observe when we photoionize in correspondence with a minimum of the vector potential, it's a downtick of the distribution. And the last interesting case is when the photoionization occurs when we have another zero crossing of the vector potential, but now with the same slope of the curve. Because for the same reason, now we don't have these compensation effects, but the two effects will add up. And so we expect to stretch the photoelectron distribution here. Okay? So this is the idea of the attosecond streak camera. The first demonstration of the attosecond streaking technique in the way I've shown you in this way was reported in 2004 by Rana Kimberger and co-workers. So and they clearly show that without CP stabilization, when you have the photoelectron distribution but no particular streaking, only when you you switch on the CP stabilization, you will start observing this oscillatory motion, which is nothing else than the vector potential of the infrared field. Okay. We also performed, this is the experimental setup we use in our labs, a few years ago in order to perform these measurements. And I just want to show some of the measurements that we performed here. Also because apart from the clear periodicity, which is reproducing the vector potential, here you can also see the clear difference between the two slopes. You can see on this side here, the intensity of the trace is larger than on the opposite one. And this is a clear experimental proof that the isolated attosecond pulses that we were creating in this condition presents a positive churn. Okay. It was good to know because we could also compress them using essentially aluminum foils, which present in this photon spectrum range, a negative dispersion. So one can use aluminum foils with different thickness in order to partially compensate for the positive chirp of the attosecond pulses. And in this way, we could create pulses which have a duration of the order of 130 attoseconds. We also applied, in order to retrieve the pulse duration, one can also apply, let's say, just not only by visual inspection of the trace, one can also apply really retrieving algorithm, the frequency resolved optical gating in this case, in which essentially you use the pulse that you want to characterize here, and you consider a gate. In our case, the gate will be given by the action of the infrared field. The photoelectron spectrum that we measure is essentially represented by this equation where we have a cross correlation between the electric field and the gate. One can run one of these retrieving algorithms, and one can cast the photoelectron spectrum in this form here. So we have the XUV field, this is the one we want to characterize. The gate is represented by the phase modulation introduced by the vector potential here. Here you can recognize the term where the velocity of the photoelectron multiplies the vector potential of the infrared field that we have seen before. And so essentially the infrared laser field provides a phase gate for the frequency resolved optical gating measurements for the attosecond pulse. This is a beautiful results, which was demonstrated by Yann Meres and Fabien Quéré with the technique that now is known as frog crab, which is, if you want, it's a kind of extension to the attosecond domain of the frog technique that was demonstrated, I mean, for the femtosecond domain several years ago. So we applied this algorithm, and that's also, I mean, important to check the quality of the measurements. And just by looking to the reconstruction, the three frog crab traits, you can, let's say, judge also qualitatively the quality of the measurements. And from this trace here, you have, I mean, all the information. You have information about the XUV pulse, the spectrum, and the phase, and also information about the infrared field. So you have really, I mean, a complete characterization of the pulses that you use in your experiments. And with this, we could characterize, I mean, now almost 20 years ago, 130 attosecond, which was, I mean, near a single cycle fast. Now, of course, the last years, I mean, there have been, I mean, a lot of progresses on generation of isolated attosecond pulses. And I was discussing before with Pascal, because I think this is, I mean, the current world record, if I'm not mistaken, no? Unless there are objections, I don't know. It was published, I mean, just 1 month ago. Yes, Electra Science.
Jens, no?
Sorry?
Who did this? It's Jens.
Yes, Jens Peters, who is also part of the net. That's good. And I mean, it could demonstrate, I mean, subatomic units, I mean, pulse duration, 19 attoseconds, using these mid-IR source. So I guess they have an, I don't remember now, I mean, you have here. They have a full width at half maximum of the spectral intensity of about 100, 150. So very large benefit. We will see. Okay. Now, let me, I just want to say something, I mean, because at least I remember when I was a PhD, it was a little bit confusing from this. Also, I mean, now considering, I mean, the Nobel Prize, which was awarded. So the very first attempts to demonstrate the generation of femtosecond pulses, isolated one, was done, I mean, of course, in the Krauss group in Vienna in 2001, where they could demonstrate they were using, I mean, I don't know if we should call these attoseconds free camera. The principle is the same. So you always look to the interaction of the photoelectron wave packets released by your XUV radiation with an infrared field. But in that case, they were not looking along the polarization direction of the infrared laser. They were looking in the perpendicular direction. Okay, so this changes a few things. The collection efficiency, I mean, the number of electrons that you will collect, and also the periodicity. You don't expect to see anymore the vector potential here when you change the delay, but you expect to see a periodicity which is twice the one of the vector potential. Okay. So in this first attempt, they could measure a pulse duration of 1.8 femtoseconds, so very close to top 1 femtosecond pulse, but not yet there. And then later on, also, I mean, in the same year, they finally managed to record this modulation here, you see, which now resembles closely the modulation that you would expect by looking in the perpendicular direction. And by doing a comparison between simulation and experimental data, they could retrieve, I mean, these finally the very first measurement showing, I mean, an XUV pulse with the duration below 1 femtoseconds. Okay, so the very first measurements were done with a perpendicular geometry, but as far as I know, no one is using this anymore. I mean, I might be happy if you correct me. I don't know.
I didn't know. I didn't notice.
Yeah.
Yes.
And the other interesting point, I mean, now also if you compare the dates, the first measurement with CP stabilized pulses, again, the first group was done in 2004. The first measurement was done in 2001. So it means that the pulses here were not CP stabilized. And I remember, I mean, it was beautiful to see the evolution because I think probably Pascal remembered, but I remember a paper from Mettegard. I don't remember the year, in which he was showing that in this experimental condition, that's a correct results because in the largest majorities of shots, they were really creating an isolated attosecond pulse, even though they didn't have CP stabilization. Also by spatial selection of the harmonics. I think it's an optics letters which appears a few years later, where really, clearly, put on a very solid basis, this result. Okay. I like to say this.
I didn't know that they were perpendicular. Okay, I never noticed this.
I think the reason why they were using perpendicular, it said in the paper, it's because they were afraid of ATI. To have, a strong contribution of the ATI. This is what I inferred from the text in the manuscript. But also when we did, in the field now, several groups have done this. That seems to be a major issue here. Also, if you measure, along the parallel direction. But it can work.
Because usually you expect a very negligible, very slow signal in this case.
Yeah.
Yeah.
It's nice to see how things evolve.
Yeah.
Okay. Yeah, this was I was mentioning. The very first, CP stabilized XV spectra from a few years later. Okay. Now, the last part, of the talk, I would like to say a few words about metrology of isolated attosecond pulse in a 3-electron laser. FEL sources, we have seen Fermi. Today, there are, of course, other FEL operating in the extreme ultraviolet and X-ray. In Hamburg, now there are 2 3-electron lasers. The very first one which come into operation is Flash. And then there are several projects, Swiss FEL, plus actually even for Freiburg in Switzerland, Cycler in Japan, then LCLS in the US, and I will say a few words about LCLS. And now there are also projects in China, since a few years in China, in Shanghai with the 2FR laser, in Korea also. But LCLS is really the first 3-electron laser in which isolated attosecond pulses have been demonstrated and also used quite intensely. So which are the challenges related to these experiments, the one conducted at LTLS? The challenge is essentially, I would say, it's the following. Typically, with our tabletop sources, we don't have very large signal. Our attosecond pulses are rather weak, but we can produce attosecond pulses with characteristics which are reproducible from shot to shot. This is not the case at 3-electron laser, apart Fermi. So the characteristics of this attosecond waveform will change from shot to shot. And the challenge is how to maximize the number of shots in which we have really isolated attosecond pulses, and then also to characterize your temporal structure on a single shot basis. These are really the challenges. So you want to characterize with a single shot the full temporal structure of your pulse. How can you do this? The solution that were implemented at LCLS at Stanford is to use, again, streaking, but this time with a circularly polarized pulse. So I will show you now some measurements. So the idea is to have, again, this very short attosecond pulse and to do an angular streaking using a circularly polarized pulse. The idea, I like to say, this still comes from our community, where our means, from the tabletop community, because the very first suggestion was done, again, by Riconstant in 1997. And then there is a kind of extended paper, published a few years later by the group of Chidong-Ling in Kansas, where they really consider in detail this case. You have an isolated attosecond pulse, and you do streaking with this circularly polarized infrared field. And depending on the relative arrival time, you will see that you will get the streaking in the, for example, in the left direction or in the upwards direction. Essentially depends which direction the vector potential is pointing at the ionization instance. In the attosecond streak camera, as I have explained before, you have just, the amplitude of the vector potential along the line. Here, the vector potential is rotating around the circle, and so the photoelectron angular distribution will rotate. They have also shown that from this information, you can nicely reconstruct again the amplitude and the phase of the attosecond pulse. In other words, you can reconstruct the electric field of your attosecond pulse. And this is essentially the idea that was implemented at LCLS. Kind of complicated experiments also regarding the tail detection, because they had to develop a linear VMI, velocity map imaging, in order to be able to measure on a single shot basis this photoelectron angular distribution. So the setup, in a few words, looks like this. You have the X-ray, which are linearly polarized. They propagate through an Ole mirror, and this Ole mirror will be used to recombine the X-ray radiation with an infrared pulse, which presents circular polarization. The two pulses are then focused here inside a gas jet, which is also the source point for this collinear velocity map imaging. So the axial, this axis along which the pulses are propagating is also the spectrometer axis of this velocity map imaging spectrometer, and you collect the photoelectron angular distribution on this MCP here. Okay, the geometry is different from the traditional velocity map imaging. And these are the measurements, some example of measurements that were acquired. So you see here this white spot, this corresponds to the region where, essentially the XUV and infrared radiation are propagating through, region through the NCP. And around you see these two lobes, and already the observation of the two lobes is an indication that they were measuring an isolated attosecond pulse. And the position of these two lobes will rotate depending on the specific shot, because this depends on the arrival time between the X-ray pulse and the infrared radiation. Based on these measurements, which is acquired on a single shot basis, they can run a reconstruction algorithm, and they can reconstruct the pulse duration of the X-ray radiation. And in this way, they were able to show that typically when using X-ray radiation with a mean energy around 900 eV, the pulse duration was on the order of 300 attosecond. Pulse duration are a little bit longer when they are using a lower photon energy on the order of 570 eV. They are more around 500 eV. The other important point is not for all shots, because of the generation mechanism, you don't have always an isolated attosecond pulse. With this approach, you can have also two and also longer pulses. So one needs really to sort out the data in order to extract only those corresponding to an isolated attosecond pulse. Okay, and then construct this histogram in which we have the number of counts and the corresponding pulse duration. So the way we are analyzing the way the data at FEM, it's, I would say, different because, the characteristics of the XUV radiation are reproduced from shot to shot. Okay. But again, the idea behind it's still an attosecond streaking, but done in a slightly different way with respect to what we usually do with our tabletop sources. And I think, that's everything for my side. It was a long day, and of course, I'm happy about questions. Otherwise, we go for them. Thanks. Yes, Fernando. Oh my God. No.
If you want, I can stop recording if you don't want the question to be recorded.
Okay, well, I have no problem.
Thanks, Doris.
I want to know your opinion about this shot-to-shot variation. Well, we performed some calculations a few years ago, precisely in collaboration with the LCLS people, just to see what would be the effect of shot-to-shot variation on whatever dynamics you would like to study. And the conclusion was that because the pulses are so short, that you know, the shot-to-shot variation, either in the spectrum or the phase, was not so relevant. It introduced some blurring in the dynamics, but was very small compared to many other things that you may have. So I would like to know, so as far as I understand, problem of shot-to-shot variation is smaller, any, or correct?
You talk about shot-to-shot variation between XUV and IR. No.
No, between two. I mean, when you shine your attosecond XUV pulses, so you have a shot, okay, every pulse is different, you know.
Okay, this sense.
This is what I'm talking about. Okay. And so, but I mean, if you want to use this to study some dynamics, electron dynamics in atoms, then of course every pulse will generate a slightly different dynamics in principle, very different dynamics. You don't know until you perform a calculation or you perform some modeling. And this can be a big problem if the pulses are rather long. But when you go to the attosecond domain, this problem is still there, but it doesn't blur the dynamics to study. It introduces some blurring, but you know, the dynamics, so it works. And so my question is, so after me, I think this, you don't have this problem, or you minimize this problem of short variation. Correct me if
We also do a sorting of the data. I mean, to get the best quality data, I mean, you can also do a sorting of the data based on the intensity of the harmonics that we measure on a single shot basis.
Okay. So my question, just to the, so to compare with the LCLS pulses that are currently generated, which have this problem, but which at the end is not a major problem, to investigate attosecond electron dynamics, atom molecules. What would be the main difference between the pulses that would be generated here and those generated at LCLS? So this long introduction.
Should I start? I don't know if you want to add. I think one point is also, if you look to the methodology, okay, we can. I think one advantage of having, the possibility that you have at Fermi is that you can acquire over several shots, and you can really construct correlation, maps. We don't need to do the temporal characterization on a single shot basis. Okay, also the way also the Nature paper and so on. We integrate over several shots. And I think this will lead also to an improvement when we want to study dynamics in terms of signal to noise ratio. Yes, in this sense, yes. Because there are still, of course, differences because of small intensity fluctuation. But I would say these are really in the direction of what we have with our tabletop sources. Okay. Probably not so good as the tabletop source, but also not dramatically different, few percent, let's say. That's why we can also accumulate, under several shots, or reorder the shots, what we are doing with the attosecond timing tool. I don't know if this answers your question.
More or less. We can get some more detail later.
I don't know if you want to add something.
I would only add that we are still talking about an interferometric condition where the envelope of the pulse is long compared to the number of pulses, of attosecond pulses. But within, and that rules out certain experiments. You don't really have to, let's say, from attosecond experiment, you don't have separated pulses. pulse is one with that, and the pulse at the other one as a probe. But other than that, you have what you lose in terms of the you gain in terms of the phase resolution that you can which is the stuff out of that.
I think.
Maybe you will tell us in a few years something, but so
lack of understanding for my question. In the previous slide,
this one?
yeah, that this law are except the proof that they have isolated attosecond. Can I ask how it is?
Because essentially, maybe I didn't say this. Let's go back to this one. Essentially, what you can do, you can start comparing this. Let's look to this simulation here. Okay. On the bottom, what you have is okay. Let's start from here. You have each beyond, and you can see the width of these lobes depends on the XUV pulse duration, of course. Now, when you start adding the IR, you see that if you have an isolated attosecond pulse, you will still see these two lobes, right? They will start moving around, they will be pushing one direction, but you have these two lobes. If you start having long pulses where you have, no longer an isolated attosecond pulse, but for example, a few femtoseconds, you see that now you don't have just a lobe, but you have, one main lobe and then some satellites here, also on the other side. So, why this? Because you go from a condition where you have, let's say an isolated attosecond pulse, which is strict, to a condition where you start having side bands. Okay, this is not yet very well pronounced here because you are in a kind of intermediate regime. You don't have an isolated pulse, so you don't have a structure shorter than the semi-optical cycle of the optical cycle, but it is also not so much longer. But you can start seeing these additional satellites. This sense, if you see the two lobes, you are really quite confident that you have an isolated attosecond pulse or sub-half optical cycle radiation. Okay. So I think we can close here. Again, still in time.